So, we are slowly going towards understanding how ultra short pulses are produced, and on our way we have discussed what longitudinal modes are. Whatever discussion we are doing now is completely from this introduction to laser spectroscopy. This is the cover of the book. It's not very costly, 1500 rupees now. It used to be 8,000 at one point of time. So, this is what we are going to follow by and large for next few modules. So, to remind ourselves, what we have learned is that a laser is, we always think that a laser is monochromatic, but what we have discussed is that it is, strictly speaking, most lasers are not, because they comprise of longitudinal modes. What is the meaning of longitudinal modes? We said that to set up a standing wave, the essential condition that has to be fulfilled by a wave is that the cavity length L must be an integral multiple of half wavelength, n lambda by 2 equal to L. So, there can be many such modes that can be there in the laser. As we have discussed earlier, we are not really dealing with n equal to 1, 2, 3. We are dealing with n equal to very large number, 10 to the power 6, 10 to the power 4. So, 10 to the power 4 plus 1 is almost 10 to the power 4. So, wavelengths of modes that are adjacent to each other do not really vary too much. That is the first thing to understand. Secondly, we have worked out the expression for delta nu, where delta nu is the difference in frequencies of two successive modes, mode number n and mode number n plus 1, and that turned out to be C divided by 2L. And the C divided by 2L is actually an interesting quantity. What is it? C by 2L or 2L by C. What is 2L by C? It is a round trip time. Okay. So, it turns out that delta nu, the difference between two successive modes, is equal to round trip time, inverse of round trip time rather. All right. If you do not remember this, you better write it down. We are going to need this later on in this module or next. And this is another thing that we said, that if you think of the spontaneous emission band, spontaneous emission spectrum, and if you think of stimulated emission spectrum, we discussed why stimulated emission spectrum is narrower, and we said that let us say that this laser action threshold is somewhere here, and we said it is about at half the intensity. We said if the half width at half max is delta lambda, then delta lambda is going to be the half width at the base of the stimulated emission band. Okay. So, now we are really talking about not full width at half maximum, but pulse duration, which is the time for a pulse to go from 0 through a maximum to 0. Okay. Well, in this case it is not really time, we are talking about lambda, but as you know, frequency and time are interconvertible by Fourier transformation. We are going to invoke it in this module or the next one. This is another thing that we have studied. We asked that if this is the spectrum of stimulated emission, how many longitudinal modes are there? And the answer was capital N equal to approximately 4L delta lambda divided by lambda 0 square. What is lambda 0 square? Lambda 0 is the wavelength where the spectral maximum occurs. And what is delta lambda? Half width at half maximum of spontaneous emission. So, it is basically half width at base of stimulated emission band. And what was that capital delta nu that we talked about a little while ago? Delta nu, what was that delta nu? The difference between frequencies of two successive nodes. So, please do not confuse that capital delta nu with this small delta lambda. This delta lambda is for the entire spectrum, for the entire stimulated emission band. That capital delta nu is the difference in frequencies between two successive longitudinal modes. I have this bad habit of saying normal modes all the time. So, if I say normal mode by mistake, I really mean longitudinal modes here. I do not really mean normal modes of vibration or any such thing. Okay. So, this is another important quantity that we are going to use. So, if you do not remember, I do not expect you to remember it, but better write it down. It is going to come handy later on. Total number of longitudinal modes is 4L delta lambda divided by lambda 0 square. Okay. And then one thing that I would like to draw your attention to, which we did not say in the last couple of modules, is do not think that the longitudinal modes have spectra that look like delta functions. See, so far what are we saying? We are saying that this nth longitudinal mode has some frequency nu n. The next one, n plus 1th longitudinal mode, has frequency nu n plus 1. So, that might give you the idea that these are delta functions, but that is not true. Each longitudinal mode has a spectrum which has finite width. Do you agree or do you not agree with this? Let me rephrase the question. Is it ever possible to have a spectrum which is a delta function in the truest sense? No. Why not? Yeah? Why can we never get for any system a spectrum which is a delta function? And here I am talking about energy domain spectrum. Yes? So, this takes us back to the semi-classical treatment once again. We keep referring to it again and again in this discussion. Time dependent perturbation theoretical treatment of interaction of radiation with matter. So, there if you work it out, you will see that, well, of course, you have a spectrum, there are many line broadening mechanisms that can take place. Some of them are homogeneous, some of them are inhomogeneous. We are going to talk about homogeneous and inhomogeneous line broadening mechanisms later in this course, because you cannot have a course talking about lasers and not talking about line widths, and in the next couple of modules we sort of get an idea why, right. So, can we name some line broadening mechanisms? Yeah, I will tell you one: collisional broadening, right. Molecules that collide with each other, they transfer energy, and so energies change, and that is why spectral line gets broadened. Doppler broadening, somebody said. Doppler broadening is also correct. So, what is Doppler broadening? It is best understood in terms of emission. Your system emits light and it goes towards the detector. Now, if the molecule is also moving towards the detector or away from the detector, then the effective length changes and effective frequency changes, very much like what we have studied in class 11 and 12 physics, where the train comes towards you, the whistle sounds more shrill. More shrill means frequency is higher, and when the engine goes away from you, it sounds less shrill, because there is like more space in that time and the wave is getting broadened. That is called Doppler broadening. So, Doppler broadening is an important issue in spectrum, in spectroscopy. But suppose I say that I have a situation where I completely stop collisions, maybe freeze the sample or something, nothing is moving. And since nothing is moving, Doppler broadening also does not arise. Still, there is some mechanism, no matter what you do, you cannot get rid of one thing that will invariably add to line width. Let us say I have quenched vibration. Of course, I can never quench vibration because it will be in that V equal to 0 state. So, the mechanism that you cannot do anything about is natural broadening or lifetime broadening, right. It is something like, you can, if I put it very qualitatively, what it means is ground state has a lifetime of infinity, let us say, and excited state has some lifetime. Okay. So, of course, there will be some uncertainty in time, and we know uncertainty principle. Uncertainty in time multiplied by uncertainty in energy is a constant. So, what is the maximum uncertainty time allowed associated with the excited state? Cannot be more than its lifetime. So, if I say my height is 5 feet plus minus 30 feet, does it make any sense? It does not. If I say my height is 5 feet plus minus 5 feet, then also it does not make sense to me, for me, but it does make sense for quantum mechanical objects, as you can only do so much. So, that is the maximum limit on uncertainty. So, since that uncertainty is limited, you will have some uncertainty in energy also. You cannot have delta E almost equal to 0. Okay. So, speaking very, very qualitatively, that is what gives rise, that is why it is called lifetime broadening. Okay. So, some broadening will be there. Okay. So, it is important to recognize that each mode, each longitudinal mode also has a spectrum that is not a delta function. At least natural line broadening will be there. Let us say that is delta less. My problem is I have used such a color that I myself cannot read. Anyway, so delta less, spectral width of each mode. It is important to recognize that it is there. Okay. Now, next what I will do is I will take a little bit of a detour. We will come back to this mode locking business. Mode locking is the technique we want to discuss today, by which you can produce ultra fast pulses. But there is another method by which you cannot perhaps produce an ultra fast pulse, but you can produce say nanosecond pulses also. It is called Q switching, you are right. So, what is this Q? Where did it come from? Is it James Bond Q or what is it? So, most likely we will have to come back to this issue of Q, but let me for the next 3-4 minutes at least provide a glimpse of what it is. Q is quality factor, Q for quality, and it is defined like this: 2 pi multiplied by energy gained in the system divided by energy lost during one cycle. Okay. Why will energy gain be there? In a laser, I am talking about laser of course. What is the mechanism by which energy gain can take place? And when I talk about Q, I am talking about the cavity. Okay. So, what happens is, you go back to the very basics of lasers. You have this active medium that is giving out light, right, and it is doing round trips. In every round trip, the number of photons is getting increased. So, in other words, energy is increasing, right, that is called gain. And how do I get lost? I mean, I do not get lost. How do I lose energy? How does the cavity lose energy? One thing you can think is, suppose now light goes out of the cavity, that is actually a loss. Okay? That is what we want, but as far as the system is concerned, it is a loss. But for now, let us not even talk about light going out from there. If you even put 200% reflecting mirrors, will it just keep on gaining energy, or will there be some? There will invariably be some loss. Why? Because the system will get heated up. Heating is a very big problem in lasers. So, you see you have to use things like chillers and all many times when you use powerful lasers, right. There can be diffraction, there can be scattering. So, there can be many mechanisms. So, this Q is given by 2 pi into energy gained in system by energy lost. And when I say Q switching, what do I mean then? I mean that for some time I let the Q go up, right. That means energy is getting built in the system. Then by some mechanism I switch the energy out. So, what will happen? At that instant Q will fall, right. So, Q will switch from a very high value to very, very low value. Okay. Then again Q will start building up. So, if you can somehow achieve this, that is one way of producing pulse laser, Q switching. How we achieve this? We are going to discuss when we talk about the actual instrumentation part. All right. But the point is, since there is some loss, it is no longer fair to think of this wave that I have as just a plain wave, right. It is going to be sort of a damped oscillation if there is a loss, right. So, it will be something like this. Do not worry too much. The purpose is not to do every bit of math that is associated, but rather to get a working idea. Okay. So, we will take things axiomatically, but these are not all that difficult also. So, something like this, you have an oscillation and there is a decay, and this figure here is not really to scale. It is not to scale, because this T0 that you see, T0 is basically the time difference between two maxima, time interval between two successive maxima, and tau is time for decay of amplitude from A0 to A0 by E. Does that ring a bell? It's sort of something like lifetime, time constant, right. Now, generally T0 is actually much smaller than tau, otherwise you have a very bad laser, all right. If it decays completely even before doing a cycle, then how will you work? So, this figure is just is not to scale, it is done in such a way so that you can see all the quantities involved, that is all. But T0 is actually much smaller than tau, and we are going to use it shortly. But let me write something, let me write this 2 pi, then what is energy gained in the system? A0 square. What is energy lost in one cycle? It will be A0 square minus A0 square into e to the power minus 2 beta by T0. For now, do not worry about what beta is, we will have to come back to that. We can go to the final expression, A0 square will cancel between numerator and denominator. You are left with 2 pi divided by 1 minus e to the power minus 2 T0 by tau, which is a very familiar form of equation for us, right. Okay. Now, we can simplify this expression a little bit, precisely because T0 is so much smaller than tau. So, what will happen if T0 is much smaller than tau? How do I expand e to the power minus 2 T0 by tau? Now, this is a technique that we have used in almost all physical chemistry courses, right. If you do quantum mechanics, statistical mechanics, whatever, you always use this kind of an approximation. T0 is much smaller than tau. So, how do I expand e to the power minus 2 T0 by tau? E to the power minus x when x is very small? 1 is correct? Yes. So, I can write something like this. Of course, there are higher terms, but as it always happens, higher terms are, we are saying that this itself is very small. So, higher terms will be even smaller. So, we neglect them. So, we can just put e to the power minus 2 T0 by tau to be equal to 1 minus 2 T0 by tau. And if I take this expression and plug it into the expression of q, what will I get? Very convenient, 1 and 1 will cancel each other. What am I left with? Yeah? Something like this. Okay? Now, so 2 and 2 will cancel, of course. 1 by T0, what is T0 is time period, right? What is 1 by T0? 1 by time period? Frequency naturally, and of course, the answer is also in front of you. Pi nu 0 tau, okay? And then pi nu 0 is the angular frequency. We are going to use angular frequency time and again here, because we are dealing with periodic functions. They are going to repeat after regular intervals. So, angular frequency very often turns out to be an easier parameter to use. So, you get omega 0 tau by 2. Okay. Now, next part I am not going to derive, I will just tell you that delta less, what is delta less? Spectral width of each mode is given by 2 pi into omega 0 by q, okay? 2 pi into omega 0 by q. So, this is the expression for spectral width of each mode. The purpose of this discussion is twofold. First, to emphasize the fact that longitudinal modes do not have delta function spectra. Second, to introduce this important parameter, quality factor q, which plays a very important role in producing larger pulses, and also, as we will see later on, the same kind of device is used when we want to amplify a laser. So, q factor is something that will come back again and again. Now, let us come back to our discussion where we had stopped in the last module. We said when we take longitudinal modes in a bunch, what do you expect to get? And we have talked about two situations, one in which delta phi is constant. What is delta phi? Phase difference between two successive longitudinal modes. Constant means it is independent of time. And second one where delta phi is a function of time. So, let us take the second one first. If phase difference is a function of time, then you have a very chaotic situation, right? There is no correlation, now it is there, now it is not there. So, you are going to get something like this. Okay, you are going to get a free running laser with inherent fluctuations that might be there. However, if delta phi is constant, then what happens? We discussed it in the last module, but we did not really spend too much of time on it. So, for the benefit of those who might be new to something like this, it is not very difficult to understand first of all. It is understood quite simply by using simple day to day analogues. Okay? Think of a team of runners, 5 runners, and they are running around a field, running around gymkhana. They start together. When they start together, they are in phase. Okay. When they start running, somebody runs faster, somebody runs slower. What will happen? There will be a spread, right? And then it is possible that they are going to come back all together. If they keep on running at the same speed for a long time, there will be times when they come together, there will be times when they move away from each other. It might be difficult to believe if I am talking about 10 runners, but it is absolutely easy to understand if I talk about 2, right. Suppose Shorodip and I run a race around Gymkhana ground. What will happen? Of course, he will win because he can run faster, he will not win. Okay. So, let us say Tanuja and I run a race, Tanuja will definitely win, right. So, what will happen? We will start off together, then we are in phase, right, and then what happens is Tanuja starts taking a lead and I start lagging, and then if our speeds are sufficiently different, what will happen? Eventually she will catch up. I will have done 5 laps, she would have done 6 and she would have caught up with me. Okay. So, that time we are again in phase. Whenever we come together, we are in phase. When we start moving away from each other, dephasing starts, and when we are diametrically opposite in the field, that is absolute destructive interference, right. So, now just extend this to many runners. That is exactly what happens when delta phi is constant. Well, what I discussed is when delta phi becomes 0, delta phi equal to 0 is easier to understand perhaps. What will happen is at this time, let us say all the waves are in phase, all the maxima match. Then what will happen? X axis is time, they have different frequencies. So, when you go away from here, some of these amplitudes will decay slower, some of these will decay faster. Okay. So, phase difference is there, but then what will happen is you don't have constructive interference anymore. Okay. So, if you look at the resultant amplitude, that is going to fall. It might do some beats up and down and then it will become 0. After some time, they will come together once again. Okay. This is something that you encounter very frequently when you discuss things like NMR spectroscopy in time domain, then you talk about interferograms. So, the important thing here that we are going to use is y axis is amplitude. What is the relationship between amplitude and intensity? What is the relationship between amplitude and intensity? Actually, mod square. Field does have an imaginary component. Okay. So, mod square. If I take mod square of something like this, what will I get? Everything will be positive, right? It will become sharper. So, we get something like this. Okay. And as we are going to see in the next module, we do not exactly get something like this, we get a little more structure in each of the pulses. So, but the crux of the matter is you get pulsed operation, and we are going to show in the next module that separation between 2 pulses is going to be 2L by C. So, what I have written this may be a little confusing. Did I see the opposite? Okay. A star means complex conjugate. So, separation is going to be 2L by C, round trip time, which is great. This is why we can do Modelocking actually, because separation between pulses is actually a round trip time. And then pulse duration, as we are going to show in the next module, is 2L divided by Cn. What is the meaning of n? Capital N? number of longitudinal modes that are locked. This is what brings us to mode locking. If we can lock a large number of modes, then we get short pulses, because see n comes in the denominator. No? If n is large, then Tp, the pulse duration, is going to be small. If n is small, then pulse duration is going to be large. So, what do you need? Do you need a single mode laser or do you need a multi-mode laser? You need a multi-mode laser. What is the meaning of a multi-mode laser? If I put it in simpler terms, the bandwidth should be large, right? When I say bandwidth here, I basically mean the spectrum should be as broad as possible. If the spectrum is too narrow, then that will mean you will have lesser number of longitudinal modes there. So, that is one essential condition. That is why it is not so easy to make an ultrafast laser using a gas as an active medium, because it has very sharp lines. You need something that has a broad spectral band, otherwise it will just not work. And so, we see that they are related to each other. An ultra short laser is always going to be a broader band laser. So, if you we are going to go back to the lab and we are going to demonstrate, the way we know that our laser has become pulsed is that we are going to discuss how you can measure the pulse width also using something called autocorrelator, but we do not even do that. All we do is we look at the spectrum. If the spectrum is very narrow, then we know that it is not pulsed. If the spectrum is broad, then we know it is pulsed, right. So, in the next module, which is going to be perhaps a little smaller than what our modules usually are, we are going to sort of derive these expressions, even though T equal to 2L by C might sound an obvious conclusion, but we will still derive it. But while deriving it, we are going to jump steps, we are going to take things axiomatically. The idea is we want an overall picture of why things are how they are. And another thing that we learn is that the way we have drawn it here is actually a simplification. You get a picture like this when you lock a small number of modes. When you lock a large number of modes, you do not get something, you get something that looks a little different. That is what we are going to discuss.